Calculus is called the mathematics of change. As this course goes on, we'll be looking at change in many different ways, but I'd like to give you an example that you're familiar with in everyday life. Suppose you have a car and you drive the car for a certain length of time. So maybe you start your trip at 2 o'clock and at 3 o'clock you've gone 50 miles. We could say that the average speed that you traveled was 50 miles per hour. So we're comparing two things. We're comparing the miles that you traveled and we're comparing the time that you traveled. That's an example of a change. We could also represent that change using a graph or using an equation. So as we'll see when we're working with problems in calculus, there are many different representations that we can use. And as we go on through this course, we'll see how all those representations are tied together and how we can interpret them. Before we get into calculus, we're going to review some algebra concepts that are going to be important to know as we move through calculus. And we're going to start with this one. A function is a correspondence between a first set, called the domain, and a second set, called the range, such that each member of the domain corresponds to exactly one member of the range. Now we can have a correspondence that is not a function, and in that case we would just call it a relation. But in order for us to be able to call the relation a function, it has to satisfy the rule that we see in this definition. Now that's pretty complicated, so let's try to make this a little bit simpler. Sometimes relations and functions are thought of like machines, where we put something into the machine and we get something out of the machine. Now we're going to be putting numbers in or sometimes variables in, and we'll be getting back out numbers or expressions. Now the numbers that we put into this function or relation are called part of the domain, and what we get back out are called part of the range. Let's take a look at an example with some numbers and we'll see if we can determine whether we've got a function here or just a relation. So let's start with an input of 2, gives us an output of 4. An input of 1 gives us an output of 3. An input of 5 gives us an output of 3. An input of 1 gives us an output of 6. Now this is not a function. The reason it isn't is because we had an input of 1 that led us to an output of 3, but it also led us to an output of 6. So we had one input of 1 that had 2 different outputs. It corresponded to 2 different members of the range. If we didn't have that last input-output pair, if we didn't have that last 1, 6, then we would call this a function. But in this case, it's not a function, it's just a relation. Now let's take a look at what we just did and the numbers we see in this table, and let's draw what's called an arrow diagram to show that correspondence between the members of the domain and the members of the range. The domain consists of the numbers 1, 2, and 5. That's all of our inputs. And the range consists of the numbers 3, 4, and 6. That's all of our outputs. The arrows are going to show how the domain values led to the range values. So for example, the first line of our table, an input of 2, led us to an output of 4. So we can show that with an arrow. In the second line, an input of 1 led us to an output of 3. Then an input of 5 led us to an output of 3. And then finally an input of 1 led us to an output of 6. Now if you look at the very top of that arrow diagram, where we had 1 in the domain, you can see what happened there. The 1 led to both the 3 and the 6. It's kind of a fork in the road. We either get an output of 3 or we get an output of 6 for an input of 1. It's that indecision that makes this not a function. Now we can also represent relations and functions with graphs. And if we do that, there is a way to figure out whether we have a relation or we have a function. And that's something called the vertical line test. The vertical line test says that a graph does represent a function if we can take a vertical line and pass it along the graph and that vertical line never intersects the graph more than once. So let's take this blue line and imagine passing it along the graph and see how many times it intersects the graph. It's never more than once, so this is a function. On the other hand, if we have this graph and we pass a vertical line along it, you can see that it touches more than once in many different places. I'll just stop it right here, and you can see it's touching that graph in 2 places. That means that this fails the vertical line test and it's not a function. Function notation is something we're going to see a lot of in this course. And if you think back to the picture we had of our function machine, you'll notice there was a letter F on it. That meant that the name of this function is F. F is a letter we use a lot to name functions, but F isn't the only letter we can use for functions. We can really use any letter to name that function. This one's called F. Now often we use the variable x to represent the input, to represent the values in the domain. And if f is the name of our function and x is our input variable, our domain variable, then f of x is what we call the output. So if we write f of x equals 2x plus 5, what we're doing is describing what goes on inside this function machine when we use a particular input value. If we want to know what f of 3 means, that means that we want to know what the output is for an input of 3. We want to know what happens to this expression, 2x plus 5, when we substitute 3 for the variable x. Now don't forget that you're always going to use order of operations when you're simplifying these expressions. So we do need to multiply 2 times 3 first and then add 6 plus 5 to get 11. So all that means is that an input of 3 gives us an output of 11. If we ask what's f of a, that means the same thing except we're substituting an a for the x. And in this case, our output is an expression 2a plus 5. Remember, you can't combine the 2a and the 5 because they aren't like terms. One is a variable term and one is a number term. And even if we have something like f of a plus h, that simply means we're substituting a plus h for the x, and we're simplifying. We're going to be doing lots of graphing this semester, but for now you just need to remember some of the basic types of graphs that you've already done in algebra. For example, you've already graphed something like this, f of x equals negative 3/5 x plus 2. Now remember, f of x really means the same thing as y, so if it helps you to replace the f of x with a y when you're graphing, that won't hurt a thing. It's a linear function, so that means that we expect the graph to have the shape of a line. There's lots of different ways to graph a line. One way would be to simply make a table of values, substitute some numbers in for x, and get numbers back out for y. And that would give us some ordered pairs. And when we graph those ordered pairs, we can see that they really do fall on a straight line, which is what we expected from this linear function. You might also remember that this particular equation is in slope-intercept form, which means you could graph this line using the y-intercept of 2 and a slope of negative 3/5. This is an example of a quadratic function. Now I know it's quadratic because of that x squared term that I see. This is a polynomial equation and its highest exponent is 2. It's a second degree equation, so I know that it's a quadratic function. There are lots of ways to graph quadratic functions. You can always make a table of values, substitute values in for x, get values back out for y, and then graph your points. A quadratic function will have a graph that's in the shape of a parabola. This one opens up, which means that its vertex is the lowest point on the graph. It's a minimum. You'll also notice that parabolas are always going to be symmetric. So if after you graph your points, your parabola looks lopsided, it's time to go back and check your points and see if maybe something is off a little bit. This is an example of an absolute value function. An absolute value function will always have a shape that's kind of like a V. In this case, the point of the V is the lowest point on the graph, and it's at -1, 0. There are lots of ways to graph absolute value functions as well. If from your algebra classes you remember something about how to look at the equation and know how this graph has shifted from a parent function, that is great. That will give you a little bit of a head start in graphing. If you don't remember that, that's fine. Make a table of values. Just be aware that since it's an absolute value function, you expect that V shape. And until you see the V shape happening when you graph your points, you probably don't have enough points in your table in order to complete your graph. So get enough points so that you can see the V and then connect the points to make that V. Now this type of function is a little bit different. It's called a piecewise function because it's defined in two pieces. The top part, g of x equals 3, is the definition for input values for x values equal to 1. And the bottom part, g of x equals -x plus 2, is the part we'll use for any input value that's not equal to 1, any x value that's not 1. So for example, if I wanted to know what g of 2 is, I would first have to figure out whether I'm going to use the top part of this definition or the bottom part. And since 2 is not equal to 1, I'm going to have to use the bottom part. So I want to use g of x equals -x plus 2, which in this case is -2 plus 2, which is 0. How about g of -1? Well, -1 is not equal to 1, so once again we're going to use the bottom part of this piecewise function definition. So g of -1 is -1 plus 2, which is +3. How about g of 1? Well, 1 is equal to 1, so we're going to use the top part of this. G of 1 is equal to 3. Now this is what the graph of this function would look like. If you look at the bottom part, g of x equals -x plus 2, that should remind you of the equation of a line, which is why you see a line in here, but there's a hole in it. And the hole is there because that line is only going to exist for x values, points that have x coordinates that aren't equal to 1. The x coordinate that is equal to 1 has a y coordinate that's equal to 3. That's the dot that you see at 1, 3. And if you look at what we got when we looked for these 3 input-output pairs, the first input-output pair we got was 2, 0. An input of 2 gave us an output of 0. That's right there on the graph. The second one was -1, 3, and that point was right there on the graph. And the third one was 1, 3, and that's this point right here. Now when we're describing domains and ranges, the way we describe those are going to depend upon what kind of numbers or how many numbers we have in the domain and range. This is an example we looked at already of something that was not a function, but it is a relation. And we could still describe its domain and range. The domain is a set that contains all of the input values, and the range is a set that contains all of the output values. So if we just have a few input-output pairs, we can describe the domain and range by just listing the values that are in those input-output pairs. But what if our domain or our range consists of a whole bunch of numbers, like all the numbers between 2 and 6, including the 2 and the 6? We can't list all of those numbers, so we're going to have to describe them a little bit differently. One way we can describe those numbers is by using what's called set builder notation. So in this case, we would say that all of those values that are shown in red are all the values between 2 and 6, including 2 and 6. So we would read this as the set of all x such that 2 is less than or equal to x, which is less than or equal to 6. The other way we could describe that is with what's called interval notation. All of our values here are between 2 and 6, including 2 and 6. So interval notation for that would be written this way. 2 comma 6, the 2 and the 6 both are enclosed in brackets. Now what the brackets mean is we are including the 2 and we are including the 6. And although this looks like an ordered pair, it has a different meaning in interval notation. It means everything between 2 and 6. So how would we describe this in set builder notation and interval notation? Now you notice we're not including the 1. So for set builder notation, we would say the set of all x such that 1 is less than x, which is less than or equal to 4. For interval notation, we want to say that we're including all the numbers between 1 and 4, but we are not including the 1 and we are including the 4. To show that we're not including the 1, we use parentheses. To show that we are including the 4, we use a bracket. Now how about this one? We're not in between two numbers. We are less than 5, or actually equal to 5. I see that that dot is filled in at 5. So for set builder notation, we would say the set of all x such that x is less than or equal to 5. For interval notation, we would say that all of our numbers are between negative infinity and 5. We are including the 5, that's why you see a bracket. But the reason why we say we're not including negative infinity is that we can never really get to negative infinity. It's not a number, it's a concept that we can never reach. And what if we want to describe the entire number line? Well, for set builder notation, we can say the set of all x such that x is a real number. And for interval notation, we can say that we're looking at all of the numbers from negative infinity to positive infinity. Remember, those parentheses mean we never can get to infinity. It's a concept that we can't reach, that we can keep moving toward. So let's see if we can tie some of these things together. Here's a graph of a function, and we want to find f of 1. So that means that we have some point on the graph where the input was 1, where the x value was 1, and we want to know what the y value is. Well, we're talking about that point right there. It has an x coordinate of 1, it has a y coordinate of 2. So f of 1 equals 2. How about if we want all the x values for which f of x equals 1? This is a different question than the first one. If we know f of x equals 1, then we know we're looking at a point that has a y coordinate of 1. And that happens right there. We want the x values where that happens, and the x value is at -4. How about the domain of f? So the domain is a set of all of the x coordinates of all the points on this graph. And there are a lot of them. The x-coordinates start right there at -5. And then they move all the way over here to +3. So if we used interval notation, we would say that the domain is from -5 to 3, including both of those numbers. The range is a description of all the y-coordinates of all the points. So the smallest y-coordinate we see is at -1. And then we have y-coordinates that get bigger from that and go all the way up to 4. So the range is from -1 to 4, including both of those numbers. It gets a little trickier when we have an equation. We want to find the domain of this function. This is called a rational function, and we will learn how to graph these. But for now, we're just looking for the domain. We want to know what are the values for x that we can use as input values. The problem is this is a fraction, so we have to make sure that the denominator never equals 0. That's the only number that will be excluded from our domain. So let's figure out when that denominator is equal to 0. Well, that happens when x is 5/2. So 5/2 is the only number we cannot have in the domain. It's the only number we can't use for an input here. So we can say for set notation, the set of all x such that x is a real number and x is not equal to 5/2. Or if we use interval notation, we would say this, that the domain is from -infinity to 5/2. Union, meaning we're putting these sets together, 5/2 to infinity. And you notice we are not including the 5/2 because we have parentheses there instead of brackets. One last problem. Let's find the domain of this square root function. Well, one thing we know about square roots is that we do not want the number underneath that radical sign to be negative, because if that happens, we have imaginary numbers. So the function isn't real when the radicand, that's the 4 plus 3x, is negative. So we have to make sure that the 4 plus 3x is not negative, which means it needs to be 0 or bigger. If we solve that inequality, we see that x has to be greater than or equal to -4/3. So our domain, if we write this in interval notation, is from -4/3 to infinity. And yes, we can include the -4/3 because that's a number that makes the radicand equal to 0. And it's okay to take the square root of 0 in the real number world, all the way up to, but not quite getting to, infinity. As you can see, we have a lot of reviewing to do before we get started on calculus, but I hope this has allowed you to remember a few of those things from algebra that are going to be important as we move on.